Hey everybody, how's it going?
Good, how are you?
Yeah, I'm all right. I'm all right. Much better than Monday. Monday was no good at all. There's a new argument analysis assignment, and you also have some notes from me regarding the first argument analysis assignment, like really spare, because as I've mentioned before, like those things they're drafts. And they're graded primarily on the basis of completion, mostly because like I can't like look around here and know there are 3 more sections of this class, and that's how many assignments I have to grade. It's ridiculously too much for me to give substantive feedback for each one. But if you want to follow up on what I did post for you, please do come see me in my office, email me, let me know how I can help you. That new argument analysis assignment is about vaccines, right? Specifically the measles, mumps, rubella vaccine. Yes? I believe I have. If you're missing a grade, let me know. You shouldn't be. Okay. All right. It's possible that I like almost finished and then, I don't know, got distracted by something shiny and didn't quite finish. That would not be me at my best, but it's been known to happen before. That argument analysis on vaccines is asking you to do something similar to the first one. It's give me the best available argument one way, give me the best available argument another way, and then as a third step, give me an argument that tells me which of those 2 arguments that you just gave me is the better argument and why. And that vaccine, I don't know if you can, like, if you could have spotted it right off the bat, but this topic is one that potentially brings in all of the stuff that we've been doing lately. The idea here is one of the biggest complaints about the safety of the measles, mumps, rubella vaccine comes from folks who say it causes autism, or it's a cause for autism. This means that there is going to need to be some sort of causal argument that's examined, right? And what's our tool for looking at causal arguments? Generalization is one type of argument, but enumerative generalization isn't quite the same as a causal argument. Generalizations are totally, like, they might slip into the mix as well, but yeah, what else do we have? Mills methods, right? Yeah, that method of agreement, method of difference, method of agreement and difference, method of concomitant variation, which I suspect will be the sort of thing that, like those methods will come in handy in analyzing claims about whether or not vaccines cause autism. Additionally, there are going to be competing explanations for the available data. So it's not just going to be these questions about, like, what does Mills' methods tell us? Like, are there some sort of, like, robust correlations going on here that I can tease apart so that I can start talking about a causal link and not just some sort of generalization? But also, there are going to be additional questions about how to interpret that data. We're going to be interpreting according to competing explanatory theories. So that business of critically comparing competing explanatory theories is also going to come into the mix. And how do we do that? What's our tool? What's the tool in our box when we have to critically compare 2 or more competing explanatory theories? Inference to the best example, that's the style of argument. And how do we evaluate our inferences to best explanation? Yes? Yeah, all those criteria of adequacy, right? Consistency, which is the big one, that big, like, consistent with the available data. And then after that, what are they again? Like simplicity, scope, consistency, scope, simplicity, fruitfulness, I heard, testability, and conservatism. Right, okay. So that's another tool in our box. There's going to be a strong temptation, I suspect, mostly because I already saw it at work in that free response question about making, make a generalization. Most blanks are blanks, make a generalization and support it for me. And I mentioned, I think when we talked about this, and some of the ways that people stumbled on that question was sometimes they turned it into an appeal to authority. They said, here's my generalization, and my justification for it is that science says, because science says so. And this is a very tempting sort of way to engage in and perhaps there's something to it as well. If there's scientific evidence, or if there are scientific studies, or if there's like an overwhelming consensus of scientific experts on something, then for sure we should totally pay attention to that, and that can count as a reason. We're going to talk about that as an appeal to authority on Friday. But today I want to do better I want to give us some tools for doing better than just saying, well, because science. Like, why do you believe that? Why is this theory better than this other one? Because science. At best, that's a shorthand for a more sophisticated answer, right? And we can totally see how people can be sloppy and irresponsible with like, well, but because science. Science works for a particular reason. When it works for a particular reason. And understanding what makes it tick and what makes it not do so well is going to help us to be able to identify when a scientific study is giving us some sort of reliable information and when it's not. So today we're going to be talking about scientific reasoning. This is another one of these topics where it's just kind of like, are you kidding me? We're going to do like all of how science works in one day, in 50 minutes? Pfft, come on, this is like a whole semester at least, perhaps even like a whole 4 years as a science student, right? That it might take to figure out how science gets done. Maybe you might even want to go to graduate school and like study the science of like how science gets done, the social science of how science gets done. Maybe a philosophy class on like the philosophy of science, which we offer, and I'll be teaching. So that's a thing. This is another reason why it's kind of like a little bit painful to try to do this in one day, because like I've got in my mind like 7 different syllabi for like a whole semester long treatment of this question of like, what are we doing when we're doing science? So the really crash course version of this today is going to start here. Just with this identification that like science is not perfect. We are in the realm of likely reasons here. That it's possible that science can get it wrong. But it's the best game in town. Asterisk. Best game in town for what it does well. If it sticks to the sorts of things that it does well, and it does them well, then science is incredibly reliable, and usually the most reliable thing that we have at our disposal as a method of inquiry for trying to figure out what we should believe. Not just us personally, but what we should, like, as a community, have as an agreed-upon set of facts. Scientific theories are explanations. Any theory is basically an explanation of the available data. The data has been collected. We're looking at that data. We've made some decisions about what in the data is important to look at, what in the data is the sort of stuff that needs to be explained, and we've come up with an explanation. And usually, hopefully, if an explanation is done well, other competing explanatory theories have been considered and weighed against one another. So this is part and parcel of the conversation that started with talking about causes and then moved on to talking about explanations and what makes an explanation work. And now we're talking about a very special case of offering up explanations, and that's coming up with scientific theories. So some of the objections that we might hear to I don't know how much trust I want to put in science. And a little bit of skepticism is probably a good idea. Most scientists have a little bit of skepticism. But some folks might say that science is a liar sometimes. Any Always Sunny in Philadelphia fans? Yeah, there's a great clip. In fact, I'm not going to play it here mostly just because there's a little bit of salty language in it. Not that that's ever stopped me before with something. But if you want to check this out, there's a little video clip from an episode of Always Sunny where one of the characters basically says, creationism is a better theory than evolution because science is a liar sometimes. It's great. It's hilarious. Check it out. So, science is a liar sometimes. We can point to all the places where science has gotten it wrong. In fact, the best available scientific theories of the day ended up being overturned, put on their head, making us all look silly. Sure, that's true. But another way of talking about this is that science self-corrects. Is that, like, when it gets it wrong, the way that we know that a previously held scientific theory was wrong was that a new and better scientific theory came along. So, sure, I suppose, science is a liar. I don't know, a liar seems a bit strong. Science gets it wrong sometimes? Yeah. You know how we know? Because science. Science tells us that the previously held scientific theory was wrong. This is how we do it. In fact, a lot of scientists will point to other ways of coming up with explanatory theories, pseudoscientific theories, we might say. Sir Karl Popper was really big on this, about like the difference between science and pseudoscience. This is a big problem in the early 20th century philosophy of science. How can we make a clear demarcation between legit science and stuff that is just pretending? And Popper says, if your own method can't undermine its own results, if we don't have something like falsifiability, if we don't have testability, this comes back to that testability criterion, then you're never, like once you settle on a theory, you're never going to have occasion to change your mind. One of the things that he picks out is Freudian psychoanalysis. And he says the Freudians, and this is for sure like a horrible reduction of Freudian psychoanalysis, but it's not too far off. Freudians will say, oh, Adam, you have a secret repressed Oedipal desire to sleep with your mother and kill your father. And I'll say something like, no, I don't. No, that's gross. I totally do not have a secret repressed desire to sleep with my mother and kill my father. And then the Freudian psychoanalyst says, oh boy, that must really be a strong Oedipal desire. Look how hard you're repressing it. You don't even know. In fact, the more violently I reject it, they're like, oh, I've touched a nerve, haven't I? And you're just like, well, like we can't win here, right? If I said, like, I do, you're right. I totally want to sleep with my mother and kill my father. Sorry, Dad. Sorry, Mom. Sorry, everybody. If I say that, then the Freudian's like, haha, I was right. And if I say, no, I totally don't, they go, whoa, look at this guy. Of course, yeah. And Popper says, this is not testable. There's no way to fail. There's no way to fail a test for this theory. And this is what makes it pseudoscience. All right. There was a hand up. Olivia, you had your hand up. And I totally steamrolled you.
Just when people say, because science, sometimes they're referring to the physics of something or the biology of something, but science is usually more the process of how it comes out.
That's right, yeah, because science, yeah, and part of the issue there is because science is it's too short to be really informative, right? Like, if we say it's a promissory note for some longer explanation, because science, and here's what I mean by that, it's vague as to what that might mean. It might mean a blind faith in whatever scientists say. It might mean, like, a scientific study was done that showed this, and we'll talk about this we'll talk about this hopefully soon. This idea that, like, just one study all by itself is, like, don't trust that. That's crazy. You need more than one study in order to, like, say that something is well-received scientific evidence or, like reliable scientific evidence or a reliable scientific theory. Okay, so first one is, but science is a liar sometimes. And we go like, yeah, the way that we know is that, like, it corrects itself, and that's a good thing. That's a testable way of coming up with explanatory theories. We also might note that, like, not everything can be studied by science. There are some notable topics where, like, science just, its tools don't work there. One that comes to mind, like, pretty readily from my own personal sort of professional interests is ethics. Ethics seems to be something that, like, I'm not sure if science does it really well, mostly because science makes descriptive claims about how the world is, and ethics tries to make prescriptive claims about how the world ought to be. And that gap between how things are and how they ought to be is enough that we can say, like, science just doesn't study this thing very well. If we can study ethics, we need to do it with a different sort of methodology. Some folks will talk about religious faith as something that, like, science just can't do the sorts of things that religious faith does. And we might very well say, like, yeah, that's probably true, although we want to look out for places where the sorts of beliefs that we have through religious faith conflict with the sorts of things that science can produce empirical evidence about. What science does really, really well is settling disputes about how the world is by showing us empirical evidence for the senses, about how the world is. And as long as we're talking about, like, a problem that can be addressed through that method, then frequently science is going to be the best game in town that we have for settling that dispute. The last thing that we might note is that scientists they're only human, and they can be biased sometimes. They can be biased in terms of, like, pet theories. Sometimes we get accusations that they're biased in terms of coming up with the sorts of results in their studies that will get them more funding. I don't doubt that some of that goes on. I will say that my personal experience with people who are practicing scientists is that they value being as objective as possible really, really highly, and they try real hard. But as we'll find out when we talk about bias, trying really hard doesn't necessarily make your bias go away. This is all true. But it's also true of any other form of human inquiry. We all have these psychological biases. They're always going to creep into the ways that we ask questions and the ways that we try to answer those questions. And on top of that, science has some remarkable sort of methodological mechanisms in it that make really impressive efforts to reduce any of that bias. Some of that has to do with things like repeatability. It's not just that I came up with it. I put the results out there and I ask the rest of the scientific community to disprove what I'm claiming. And if they can't, then that's usually good news. And if they can, now we have a discussion. Yeah?
Your example of ethics, are you familiar with the Piltdown man?
Piltdown man, yeah.
It was 40 years before science corrected itself, but it would not have been corrected had it not been for ethics.
Ooh, we should talk about that story a little more. I'd be kind of curious to hear more about it after class, or in an email or office hours or something like that, because we're kind of action-packed here today. Yes?
So I was going to ask, sometimes science kind of goes into the realm of where descriptive claims can be made, like with climate change and things like that, where descriptive observations about the world around us, but then
and then that's instrumental in then making some sort of prescriptive or normative, or evaluative claim, right?
Okay.
Yeah, we can. What we're going to need, as we discussed when we looked at moral arguments, what we're going to need is like one extra premise. And usually that's where the trouble comes up, or that's where the bodies are buried, or that's where people might disagree. One extra premise that gets us from how things are to how they ought to be, right? So for example, we might notice that the Earth is getting warmer. We might even agree upon some sort of scientific explanatory theory for why the Earth is getting warmer. There's still an open question about so what should we do about it?
So what should we do is, I guess, where the prescriptive...
That's where the prescriptive, that's where the argument can turn prescriptive, because you have this question about what should we do, and somewhere in there is going to be some idea of what's the difference between should and shouldn't. So one of the questions that we might ask about climate science with respect to how do I turn that into some sort of prescriptive claim is I might say something like, we might have questions about exactly what we owe to future generations who don't exist yet. I don't know them. They don't even exist yet. What should I owe them? What do I owe anybody else, right? And how to, and other questions that might come up in what should we do about it might fall into categories about who's responsible for fixing a problem when we look at who's responsible for causing the problem. Is everybody responsible for fixing the problem, no matter whether they were participating in causing it or not? Are the people who caused it more responsible for fixing it than others? So all of these new ethical questions are going to enter in, and we're going to have some premises that'll do that work in addition to the scientific claims. That's true. Yep. Any more questions about this? All right, that's only the first slide. Let's get going. So the first thing that maybe we'll talk about is something that, my guess is you've heard this before. You probably heard this in elementary school. This is one of the more painful moments for me in this lesson because it's way more complicated than this. Sometimes folks will talk about the scientific method. At the very least, I think we got to back off and talk about a scientific method, or a variety of scientific methods that seem to share some sorts of properties. Science gets done in lots of different ways depending on the domain of inquiry. So for example, some forms of scientific inquiry are experimental. We do laboratory experiments. There are other forms of scientific inquiry where it's really hard to do experiments, like cosmology, talking about what's going on with the stars and various solar systems and galaxies. Good luck setting up a lab with a whole galaxy in it. That's going to be really, really difficult. Sometimes we'll do this with simulations and models, like computer simulations, and it's oh, that's interesting. Is that the same as an experiment? Is that maybe something different? Sometimes the way that we do our scientific methods is we go out into the world and we just look, we just observe. So some naturalists use these methods. Cosmologists, again, do a whole lot of staring up at the sky and collecting data in order to run their tests. Not so much work in wet labs, the way that a chemist or a biologist might. Also, we have social sciences and natural sciences, and they all seem to work in slightly different ways. But I think we can say that there are some general characteristics that all forms of scientific inquiry seem to have, and we should mention those. And this is going to fit more or less the scientific method that you've been taught ever since you were just a little kid. So, starting with, we got to identify some sort of problem. It starts with a question. A problem, a question, we might say an explanandum, some cluster of phenomena that we go that's weird, I wonder what's going on there. Something's got to pique our curiosity and demand an explanation in the form of a scientific theory, perhaps, or some other sort of theory. So that's our starting point. And by the way, there can be differences about whether we think certain things are important or not. A lot of these explananda or questions or problems are built on the assumption that the data that we've collected is reliable data. So we'll say, like, we have a whole bunch of data that says X. We need to explain this. And somebody might cut it off and say, like, is that data even reliable? Is that an accurate depiction of what the world is like? Was that data, is the sample size too small? Is it biased somehow? Should we even be paying attention to this? So a lot of our questions about making generalizations and general concerns about induction in general are going to fall into this question of even identifying a problem. Next, there's going to be some sort of formulation of an hypothesis, and this is where the creative storytelling explanation generation part comes in. We see this available data, we have an explanon, and we have this thing that says, like, hey, what's going on there? And we go, I think this is what's going on. And usually this is on the basis of previously held theories. This is kind of getting at that principle of conservatism, right? You start with the theories that you already have. That's your starting place. And we should probably be entertaining other explanatory hypotheses as well, even some that might conflict with our previously held theories. And once we have that, we want to figure out, like, devise some sort of test that would tell the difference between whether this theory or this other competing theory is the better explanation for the problem or the question, the explanandum that I have. So there's this derivation of some sort of prediction, some sort of what sometimes we'll call a test implication. This is the testability part of our 6 criteria of adequacy. I make a prediction on the basis of my hypothesis about how I think that test is going to turn out. Then I perform the test, hopefully well, and then I decide whether or not I want to accept or reject my hypothesis. And both are possible, because this is a method that's testable. It generates hypotheses that are testable. Cool so far on this? Does this look pretty much like ever since you were in 2nd grade? Teachers were saying, like, this is how science works. And, yeah, Beardo up here is saying, like, it's a little more complicated than that. But, like, sure, this is Fisher-Price, my first, like, how to do science kit. All right. Where most of the focus in this happens is this question of devising a test and performing the test. And so we have all kinds of, like, questions about, like, what's going to be a reliable test? What sort of experimental designs are, and this is where, like, some folks might talk about science as an art. It can't, like, where you can't really have, like, cookbook science necessarily. You have to have people who are skilled, experienced in doing a scientific experiment, so they know the sorts of things to look out for. They know how to execute an experiment, or they know how to generate a test. They know how to collect survey data, for example. They're trained in scientific methodologies so that we can trust that they are performing tests well. And here are some of the things that we need to think about when we do that. Starting off with, we need to control all of the relevant variables. If we don't control all the relevant variables, then, like, the test that we're doing is just not going to be relevantly similar to anything that I want to scale up or make a generalization about. Every single experiment, every single test where you go out into the world and you want to check to see if your hypothesis is correct is trying to execute something like a little argument by analogy, where we say, this little corner of the world stands for the entire world. Or this collection of, like, instances where I'm looking at this little corner of the world. And sometimes that corner of the world is weird. Sometimes that corner of the world is a laboratory where we keep a lot of the stuff in the world out. And we say, like, this is, like, a highly artificial version of what the world is like. Sometimes it's so artificial that it lives in a computer. It's a simulation or a model. And these are serious questions that we want to ask, because that's supposed to be making some sort of argument by analogy to more general claims that I want to make about the world. So that analogy has to hold. And that means that I need to make sure that there aren't extraneous factors that are getting in that are spoiling my experiment. Sometimes, paradoxically, this means I have to make my experiment strikingly unlike the wild in order to control all of things. This is also a big, important part of applying Mills methods. I want to look at the correlations between, like, one variable and some other variable, an independent variable and a dependent variable. And if I really want to study those, I need to get them isolated. I need to make sure that other factors aren't coming into play. So I have to control those. Some other things that I want to think about, I need to collect statistically significant amounts of data. And this is, like, standard generalization stuff that we saw before. If I'm going to be generalizing from the stuff that I saw in my test to the whole world, I need to have a statistically significant sample size. I need to make sure that I'm not overinterpreting the data. And everybody has a tendency to do this. We get the data and we're like, haha, that just shows that my hypothesis was right. But if I haven't gone through the process of really seriously entertaining competing explanatory hypotheses, then I might miss the possibility that these competing hypotheses could explain that data just as well as my hypothesis does. Which would mean that my test is not really all that discriminating. It doesn't separate one explanatory theory from another. Both of the competing hypotheses would end up being confirmed by the available data. Also, we want our experiments to be repeatable. This is fair. Do I need to explain why? This also has to do with like making generalizations. It's not just that I did it, it's that other people were able to do it too. Maybe other people were able to do it, get the same sorts of results, even with slight variations in experimental design, to show that the pattern that I've identified is robust. Not only do I want my results to be repeatable, I want them to be repeatable. And in addition to that, I want them to be repeatable. This is important. Science works well when we get repeatable results. And actually, there are some domains of science right now. If you look into some of the scuttlebutt that's going on in popular science press, there's some rumblings about certain domains of scientific inquiry where we have a repeatability crisis. Nobody's doing the labor of going back and checking on, like, a study was published and everybody keeps citing that study, but nobody's gone back and actually tried to verify it. Nobody's looked to see if that data is repeatable just yet. And that could be a problem, right? That could mean that a whole discipline is working on the basis of theories that are a little bit shaky. They could crumble at any moment. We could go to try to repeat them eventually and find out that, like, oh shit, actually it turned out like, no, it's not repeatable. Ugh. Then the whole project falls apart and you have to start it over again. Olivia.
That sounds like something that's really common in
Social sciences, yeah. Psychology is also really kind of like grappling with this right now too. Yeah, for sure. Which isn't to say that it's not to say that it's bad science. Sometimes it's the nature of the thing that you're studying is that it's hard to get repeatable results. Hard to get repeatable results is not the same as impossible to get repeatable results, and sometimes we might just say this particular branch of science or this particular domain of inquiry makes it really hard to do repeatability, and it just means that maybe you have an appropriate amount of skepticism when you look at the theories that are coming out of that science. Or you ask this question, like, was this repeated? All right, so these are some of the things that we want to think about there. One last big slide. Since we're talking about testability, I think we should probably look at this question of, like, how does one of these tests work? Testability is key to distinguishing between legit science and kind of crap pseudoscience that, like, is not producing explanatory theories that tend to be as good as science. One of the reasons why science tends to deliver such good explanatory hypotheses is that it really focuses on this testability question. And a lot of the places where pseudoscience falls down on this testability question. This is something that Sir Karl Popper really hammered on. This idea that you have to have a theory that is falsifiable in order to call it science. And by falsifiable, he means testable. There has to be a test that this theory could fail. As it turns out, things are actually really complicated when it comes to testability. One of the reasons why one of the first places that we'll kind of go and point to where we might say something like, yeah, testability is actually way more complicated than we think, is we might notice that I never really get confirmation. Not really compelling confirmation, at least. Certainly not certain confirmation. I'm always a little bit sketchy when it comes to what I might call confirming evidence from a scientific study, mostly because of the way that the structure of confirming evidence would work if I was going to draw a conclusion from that. So Sir Karl Popper, also the guy who said, like, testability is like the key to distinguishing between science and pseudoscience, he also said, by the way, you never actually get confirmation from science. You only ever get falsification. We have scientific theories that haven't been confirmed by data, they just haven't been disproven yet. There's always that asterisk hanging over any scientific theory that, like, tomorrow we might discover new evidence that would completely change our minds about this. And one of the ways that we can think about this is by looking at the structure of the arguments at work. This is what evidence that would confirm my hypothesis test would look like. I say, if my hypothesis is true, then my prediction is going to happen. I go out into the world and I check to see if my prediction happened, or I devise an experiment where I check to see if my prediction happens when I perform the experiment, or I run my simulation or build my model or however it is that I end up doing it. I show that my prediction comes true. What have I proven? Can I draw a conclusion that therefore my hypothesis was true? And if we look at the way that that argument stacks up, if H then P, P therefore H, is that any good? The slide would be better if I had made this part appear after asking you the question instead of leaving it up. I say it's invalid. Do we see that it's invalid? This is our formal fallacy of affirming the consequent. That's not modus ponens. Modus ponens doesn't work that way. If H then P, P therefore H, no. If H then P, H therefore P, that's modus ponens. But if H then P, P therefore H, watch out. That's not actually a valid argument. The fact that it's not valid doesn't mean that it might not be part of a strong inductive argument as well. But we're just pointing out that the logic of scientific confirmation is a little shaky. On the other hand, if we look at the logic of falsification, we'll notice that we have something more like this. If H then P, not P, therefore not H. If my hypothesis is true, then my prediction is going to come true. Turned out my prediction didn't come true, therefore my hypothesis must not be true. That is a valid argument. That's our old friend modus tollens. Recognize him? Is modus tollens a him? Sure, yeah, why not? Modus tollens is a him. Disjunctive syllogism is a her. But yeah, modus ponens and modus tollens, sure, why not? They're hymns. So this actually does work, and this is one of Popper's big points, is that confirmation isn't a valid sort of deductive argument. There might be something inductive going on, but notice that confirmation doesn't work quite like disconfirmation works. This is why we say that scientific theories need to be falsifiable, and we don't so much talk about whether or not they are confirmed. Popper ends up saying that science is really nothing more than a series of conjectures and refutations. And we can find all kinds of stories that illustrate this in the history of science. So a really good one comes from the mid-1980s. In 1846, a doctor named Ignaz Semmelweis was working at a hospital that trained surgeons, and also they delivered babies there. And when the surgeons in training were doing their studies, they would go and they would operate on cadavers. And then when a mother went into labor, they would run, or they would drop what they were doing, run over, deliver the baby. Once the baby was checked out and okay, they'd go back to working on the cadavers again. Turned out there was another birthing center that was not being handled by surgeons. It was handled by kind of more traditional midwife types. And they delivered babies in a building that was just around the corner. And Semmelweis noticed that a whole lot more of the mothers in his establishment, where there were guys who were training to be surgeons and then delivering babies, a whole lot more of the mothers were dying after childbirth compared to this other place, which was really embarrassing for kind of an up-and-coming medical science. They're we do things very, very well. And it turns out that no, you kill your patients, and these folks over here who are doing traditional medicine, they're doing way better. Their patients aren't dying. That's I don't know how you would compare the quality of healthcare, but doctors that kill their patients seem to tend to be worse than doctors that don't kill their patients. Unless the point is to kill your patients. I don't know, a physician-assisted suicide or something like that, right? So, what's going on? Semmelweis concocted a hypothesis, and he says, here's what I think is going on. We have a problem, right? We have some explanandum. This is curious. How come the surgeons in training are killing their patients, and the midwives around the corner aren't killing their patients? I want to figure this out. And Semmelweis said, here's what I think is going on. They're working on dead people. And when they're working on dead people, they get little bits of death on their hands. And then they go and they deliver the baby, and they get the death on the mother. And then the mother catches the death, and then the mother dies. And Semmelweis says, here's how we would test my theory. Let's get the surgeons to wash their hands before they go and deliver the babies, and see if it stops the mothers from dying. And so Semmelweis says, everybody needs to start washing their hands, and all the students are oh, why do I have to? He goes, it's for science, just do it. They wash their hands, turns out, whoa, the mother stopped dying. Was his hypothesis right? Did he have the right theory? No, he was close though, right? He had something going on. He said like, all right, so I got confirming evidence. I had a hypothesis with a prediction. We tested that prediction. The prediction turned out to be true. Therefore, my theory. And we go, not so fast. There's a competing theory that you haven't even thought of that involves germs. A whole theory of germs. Not bits of death, but like living things that will get on your hands, and then you'll pass on to somebody else, and then they'll like start living big time in that other person's body, and then that gets in the way of how their body works, and then they die. They were getting septic infections, was what was happening. So like his theory, his hypothesis, his theory was confirmed, but it wasn't quite correct. And this is an illustration of like what Popper's trying to get at when he says, we don't actually ever get confirmation, we only get falsification. Does that make sense? Okay. As it turns out, we don't even really get falsification. As folks a little later will figure out. Not really even that late. Pierre Duhem was a French philosopher who actually was around before Popper, not nearly as popular, and people didn't really pay attention to him as much. But people started paying attention to him a whole lot more when another 20th century philosopher, William Van Orman Quine, ended up saying the same sorts of stuff that Duhem had been saying. Some historians of philosophy said, like, Quine's just saying what Duhem said. But they both ended up saying, you don't even really get falsifiability in science either. And this is because we never really just test our hypothesis. We're always testing an entire worldview whenever I perform an experiment or do some sort of scientific test. For example, here's if we're going to break down the logic of what's going on according to Duhem and Quine in a scientific test, we say, if my hypothesis is true, and some other assumption that I have about the world is true, and some other assumption, frequently these are called auxiliary assumptions. So my hypothesis plus one auxiliary assumption plus another one, and who knows how many other auxiliary assumptions that go into like my understanding of how the world works. If all of that's true, then my prediction will come true. Turns out my prediction didn't come true. So by modus tollens, we know that this is false, but this is a whole bunch of things. Could be because my hypothesis, my prediction didn't come true because my hypothesis is busted. Could be because other assumptions that I haven't even thought of turned out to be wrong. Frequently we can get scientific tests that test our theories and show that like, no, your prediction did not come true, but we don't necessarily chuck the hypothesis just yet. We have what we might call like phenomenon saving or like theory saving explanations that we might sneak in and say like, the problem wasn't with my hypothesis, it maybe was with some other auxiliary assumption. One of the biggest ways that we see this, especially when we're talking about scientific results that wildly contradict what the rest of the scientific community is getting, is like immediately somebody will throw out like, are you sure your experimental methodology was done really well? Are you sure that like you didn't have some like crappy grad student who like doesn't know what they're doing spoiling your results? So that might be one of the first places that we look, is like, yeah, you had your hypothesis, plus a whole bunch of assumptions about how to perform the test in the first place. Will, you had your hand?
How do you separate prudential assumptions from scientific assumptions?
Can you give me an example of what you mean by a prudential assumption?
I believe in evolution, therefore my assumption is that I need to factor that into anything that I'm doing on a scientific basis.
That's okay, so yeah, that would count as one of your auxiliary assumptions, right? And if you can manage to maintain some awareness of it, that's good. It's good to be aware of as many of those auxiliary assumptions as possible, because when we get some sort of surprising result, we want to be able to like have some idea of like where to look for like how, like why did it go wrong? Was it my belief in evolution? Was it my belief in some other aspect of, I don't know, microbiology that led me to expect the result that turned out to not happen, right? So the answer is there isn't really much of a way to make a distinction. A lot of these auxiliary assumptions are prudential assumptions. They're good assumptions to make, or they seem like good assumptions to make. They're the sorts of things that a principle of conservatism will say, like, totally, make those, have they been working out for you well so far? Keep assuming them. To go against that good track record would just be, that would be like slothful induction. It would be irrational. Want a story about this one? Why even falsification doesn't work? This also goes back to the mid-1800s. In 1821, it was discovered that the planet Uranus, it's pronounced Uranus, from Uranos, meaning the over heavens. Anos actually means also like a ring, which is the same as anus, so it is. All right, it's Uranus. But Uranus was discovered to have a really weird orbit. Newton's celestial mechanics that had been around for about 100 years at this point had predicted that like Uranus would have an orbit that was shaped in a certain way. There were predictions that you can make for like where you would be able to spot it in the night sky on any given night. And it turned out that it didn't really quite match up with the predictions, that there were some weird irregularities in the orbit, and everybody was looking at these weird irregularities and trying to figure out, like, what does it mean? Some folks said, like, it means Newton's celestial mechanics are wrong. Like, hypothesis, prediction didn't come true, therefore, chuck the hypothesis, right? This is falsifiability, totally. You had some hypothesis that was based on Newton's celestial mechanics. It predicted that Uranus would be in a certain place at a certain time in the night sky, and it turned out that you were wrong. Time to reevaluate that hypothesis. What wasn't known at the time was that there was another planet nearby, a planet that we now call Neptune, but nobody knew about it. And it wasn't until about 20 years later, in 1846, that somebody said, like, maybe the thing that's causing Uranus's weird irregular orbit is that there's another body nearby and its gravitational field is affecting Uranus's orbit. If that were true, we would be able to spot that body. Let's do the math, carry the 1, draw some pictures. We'd be able to spot it right there. Point your telescope there. They point the telescopes there, and sure enough, there it is. Blue and beautiful, like the god of the sea himself, Neptune. Right there in the night sky. Neptune was discovered because somebody said, let's not get rid of the hypothesis just yet. Maybe we have some other auxiliary assumptions that turned out to be false. Auxiliary assumptions like there are no other, as of yet, unobserved bodies like up there that are perturbing the orbits of the things that we do know about. Does that make sense? This is scientific reasoning, insofar as it can be talked about in only 50 minutes. 45 minutes, which means we have time for a worksheet. Certainly not enough time to do the entire worksheet. Let's look at some of these and see how they work. They'll give us a little bit of practice. The homework that you're going to have is a little bit different than this. Please don't forget that you have this argument analysis draft that's due on Friday. This stuff that we're talking about here, it's relevant. It may very well come into play when you're doing that argument analysis. You might have to talk about what makes science good science, instead of just saying, because science, right? Vaccines are not dangerous because the scientists say. You can do better than that. Show me the science. Show me like how it is that they came to those conclusions. Break it down for me so that I don't have to just say, oh, because science is a liar sometimes.